Hey guys, welcome back to the fifth video of the Numpy Tutorials for Beginners series. In this video, we'll be covering the linear algebra module in Numpy. So first, we'll be calculating the inverse of an array. So over here, you can see that I've declared an array A, which is 1, 2, 3, 4. It's a two-dimensional array. Now, remember that when you're trying to find the inverse of a matrix, the matrix has to be a square matrix. That means the number of rows and the number of columns must be equal. So over here, you can see that I'm using a 2 by 2 matrix. So to find the inverse, you simply have to use np.linalg, which stands for linear algebra, and then dot inv, which is inverse, and then you simply put the square matrix inside. And then you pr print out the inverse of the matrix. So you can see here that this is the inverse for the matrix, minus 2, 1, 1.5, and minus 0.5. So this is the inverse of this matrix 1, 2, 3, 4. And if you have done linear algebra, you'll know that when you multiply a matrix with its inverse, you should get the identity matrix, where all the entries are zeros except for the diagonal entries, which are ones. So over here, I've used the at operator to matrix multiply A and A inverse. And you can see that I get the identity matrix. So over here, you can see that there's some floating point decimal places after the decimal point, but remember that it's a little off, but it's if you round the values off, you'll get an identity matrix. So yeah, this is how you calculate the inverse of a matrix. Okay, so now we'll be using Numpy to find the eigenvalues and eigenvectors of a matrix. So here I've declared a Numpy array. It's a two-dimensional array which is 1, 2, 3, 4. And so the concept of eigenvalues and eigenvectors has been covered in a 3 blue 1 brown video. So if you want to find out more about this topic, you can simply go to this video. I'll put a link to that video in the description below. So I'll just be showing you how to find the eigenvalues and eigenvectors using Numpy. So here you need to use the np.linalg.eig function. So you just have to put in the array. And remember that you have to put in eigenvalues and then comma eigenvectors. So the eigenvalues are always first. And let's in fact print that out. So here are our eigenvalues. So we have negative 0.37228 and then we have 5.37228. Alright, and then our eigenvectors are over here. Now remember that the eigenvectors in this matrix are column vectors. That means that this eigenvalue is associated to this column vector, which is minus 0.824, 0.565. All right, so this column, the first column is associated with this eigenvalue. All right, and the second eigenvalue is associated with the second eigenvector. All right. So remember that the definition for eigenvectors and eigenvalues is given over here. So our main array, which is A, matrix multiplied by the eigenvector, must be equal to the eigenvector being scalar multiplied by the eigenvalue. Alright, so the eigenvalue and eigenvectors are like pairs. So over here, the first eigenvalue is associated with the first column vector, which is the eigenvector. So now I'll be using this formula. So this is actually the definition for eigenvalues and eigenvectors. So I'll be using this formula to just prove. Okay, so now let's just run the code. So over here you can see that what I've done is that I've taken the main the main array A and matrix multiply by the eigenvector. All right, and then again it's a column vector, so that's why I have to use the colon comma 0. This takes the first column, which is minus 0.82, 0.565. All right, so this is the first column, and then I scalar multiply the same eigenvector with the first eigenvalue. All right, so this is the first eigenvalue, and these two values must be equal. So over here you can see that our matrices are pretty much the same. That if you see that these two numbers are the same and these two numbers are the same, so these two vectors are the same, so these are equal. If you want to try out the other eigenvalue and eigenvector, you can simply replace the zeros with ones, and you can see that our final results are actually equal. So this satisfies the definition over here. All right, so that basically means NumPy is correct. All right, it gives us the correct eigenvalues and eigenvectors. So now I'll be covering diagonalization in NumPy. So we'll be using the concept of eigenvalues and eigenvectors. So over here I've declared an array, NumPy array 1, 2, 3, 4, which is a two-dimensional array, and then I found the eigenvalues and eigenvectors using the np.linalg.eig function. So in diagonalization, what we do is that we take the array and we represent it in the form of PDP inverse. So basically we have a matrix P, a matrix D, and a matrix P inverse. And then if we multiply them, we'll get A. Now the important part here is that D is a diagonal matrix. That means that all the entries are 0 except for the diagonal entries. So remember that the diagonal entry for D is the eigenvalues and P will be the eigenvectors. So the eigenvectors will be put in column format. So here I've simply made a variable P and it's equal to eigenvectors because the eigenvectors are already in column so that's why we can simply use the eigenvectors provided by the np.linalg function. All right, so next we need to get D. So eigenvalues is basically a one-dimensional array with all the eigenvalues, but it needs to be in a diagonal matrix where it's a square matrix and all the entries are zeros except for the diagonal entries. So we can do this by creating a zero matrix, a zero two-dimensional matrix, a 2 by 2 matrix, and then we will loop through using I, and then we will take the diagonal entry and make it equal to the eigenvalue. All right, so this is our loop, and finally to find P inverse we can simply use np.linalg.inverse. All right, and then we'll print out P, D, and P inverse, and then we'll just multiply everything together. We should be getting A, which is 1, 2, 3, 4. So let's run the code. You can see that P is over here. So P is the same as the eigenvector, as the eigenvectors. Over here you can see D. D is a diagonal matrix where the entries are 0 except for the diagonal elements, which are equal to the eigenvalues. All right, and then P inverse is basically the inverse of P, and then when we multiply everything together we get 1, 2, 3, 4, which is our main array over here. All right, so that's pretty much it for diagonalization. If you like this video, then please consider giving a like and subscribe, and I'll see you in another video.